non-deformed tip thickness. So the distance between here to here is controlled by your what? T. The smoother you want your workpiece in the end, you have to make it what? Smaller. Yes or no? Right? You want to make it smaller, right? So this distance from here to here that is our depth of cut, or we also sometimes call it width of cut. Okay. So this T, this small t, right? So I'm not complete. So this is our U, our cutting speed, and this is the workpiece material. Okay. So in finishing, so there are two processes in general in metal cutting. One is finishing, one is known as roughing. So in finishing, okay, which requires good surface roughness, right? Good surface roughness, right? T is usually in the range of 0.05 millimeter, and it can go up to 0.1 millimeter. Okay, so this finishing is critical, because if you take too big a T value, you will spend too much time polishing the surface. Okay, and you don't want to spend too much time polishing the surface. Okay, because polishing is a very slow process. It will increase your cost ginormously. Okay, then so that is for finishing. Then in roughing, so roughing, you don't care about the surface finish, do you? Right? You don't mind it being rough. Okay, so in roughing, what we can see, okay, in roughing, which is not necessary to control the surface roughness. So you're not bothered whether it's smooth or rough. Okay, the T value is in the range between you can go between 0.1 and can go up to 0.4 millimeters per revolution. Okay, so you're not bothered regarding the roughness. Okay, now to control the process parameter, right? So now we know. Okay, so we know finishing, roughing, what is the range to use. But to go into the exact value, okay, so to control, in order to control or, okay, not just control, or optimize the process parameter, okay, the process parameter, the Johnson-Cook material equation okay, the Johnson-Cook material equation can be used. Okay, so what do I mean by that? So if we were to write out the Johnson-Cook equation again, so you guys, oh, here we go again. Yeah, so stress PL is equal to A plus by B epsilon PLN, right? So by looking at some of this feature, right, we can more or less make a very intelligent guess on what process parameter to use. Okay. Now, what I mentioned earlier is dependent on just the process. In finishing, you use this range, right? But what if you have material that are very strain hardening sensitive? Between 0.05 to 0.1, what is it, right? So to know what is it, that's where you have to use what? Johnson-Cook, because it can optimize what? The process for you. And also a very intelligent guess on process parameter, okay? So 1 plus by C natural log epsilon dot ref, right? And then 1 minus by theta ambient over theta melt minus by theta ambient, the whole thing M, right? So the A value, right? The A value, by looking at the A value, you can decide on what rate angle to use. Okay, what is the rate angle to use? And then the B and N, okay, B and N, it can also help you to decide your undeformed chip thickness. Right? Your undeformed, what is your range of undeformed chip thickness you could use? And it can help you determine your cutter path. Okay, as I said, I'll talk about cutter path later. Okay, and then by looking at epsilon or your strain rate sensitivity, we can look at the range of cutting speed. Right? And then by looking at this value over here, right, the M, it can also help you determine the magnitude of cutting speed. Right? So the magnitude is different from the range. Yeah, the range you look at minimum, maximum. The magnitude is sometimes you can go faster. Okay, sometimes you can go faster by looking at it. I will give you an example later on. Or if an external heat source is required. Right? So if your material is very hard, okay, it's very hard, would help if you use a laser to soften the material. Okay, use a laser soft. So that's what we call laser assisted what? Turning. Okay, so as you can see, A, B, and N, this is our strain hardening, right? And then the other one is strain rate, right? And the last term over here is our thermal softening, right? Okay, so we are going to step into our strain hardening first. We're going to look at our strain. So we're going to talk about how the strain hardening will affect process parameter like rate angle and undeformed chip thickness. Okay, so what? Right. So we are going to look at strain hardening. Okay, we're going to look at so high strain hardening material. So if you look at this material, they are very high strain hardening. They are usually the nickel base super alloy. Okay, alloy, ALLOY. Okay, so these are arrow used for aero engine. Okay, then you also have stainless steel. Okay, they tend to strain harden very easily. So low strain hardening sensitive material. Okay, low strain hardening materials. So they are like your copper. Okay, so they are like your some of them are like your copper, brass, low carbon steel. Okay, so these are some of the example. So the strain hardening, as said earlier, like I said before, the strain hardening behavior of any material right can affect the selection of rake angle, undeformed chip thickness, and cutter path. Okay, how the two should move. Okay, so let's look at the A. Okay, so the A, okay, the A constant in Johnson-Cook material, Johnson-Cook equation, right? In Johnson-Cook, I just went over equation, were influenced the selection of rake angle. Okay. So as you now you know what's a rake angle. Now you go back to the diagram. So the rake angle, which is called alpha. So the range of rake angle can be minus 20 degrees, and it can go up to positive 15 degrees. Okay. So that is the range. Okay. So how will this A value affect what value to select? Okay. So for now, what I'm going to propose is we are going for a break. So after the break, you come back, we carry on. Okay, we are going for a break. Thank you. Come back at 4:15. Thank you.